Okay, let's make a start. So we'll finish off this short introduction set of slides, and then we'll move on to the main sets of slides, which start with electrostatics. So we finished off discussing applications of EMT. Now, in physics, we have a number of forces. Okay, so the gravitational force is the one that you know pretty well. Okay, it's always attractive and varies inversely as the square of the distance. Okay, then we have the electromagnetic force, and that's what EMT is based on. Okay, and we'll see that that's much stronger than gravity. Okay, and you can have attraction and repulsion. Again, like gravity, it varies inversely as the square of the distance. Okay, and this electromagnetic force is the strongest force in nature that we encounter in everyday life. Okay, there are a couple of other ones. There's a strong interaction force, which is stronger than electromagnetic force, but it's something that only acts over very small distances, and that's what's responsible for holding the protons and neutrons together in an atom. Okay, we also have something called the weak interaction force. Again, it's something that only occurs on over distances of like the size of an atomic nucleus. Okay, so this electromagnetic force is really the strongest force we see in everyday life. Okay, so we'll see as we go through the course that all of EMT is really just based on a number of experiments and observations which were done perhaps in the 18th or 19th centuries. Okay, and the main first one that's we'll come across is these experiments done by this guy called Coulomb, who was a French guy in the 18th century that worked on torsion balances. Okay, and he could actually measure the force between these little charged balls with these torsion balances. Okay, and that leads to something called Coulomb's law. We also had a bit after that another French guy, Ampere, and also Faraday, looking at two parallel wires carrying currents and seeing that there's also force between them. Okay, and that leads to stuff called Ampere's law. Okay, and then we also had first of all Thomson, and then Lorentz was the guy that formulated it correctly, looking at electrons moving in vacuums and how they experience forces. Okay, Lorentz force. Okay, so all those things, and also electron stationary next to a wire, electron stationary next to a straight wire, experience forces. So these are a bit close to Ampere's law, but developed by Faraday. So these observations all lead up to or actually are what EMT is based upon. Okay, so these basic observations. Okay, and also materials. Okay, we'll see that as we said, I think I said earlier that EMT is based on sources, fields, and materials. Okay, so certain ways we can bring those into the equations. Okay, here we are. So Maxwell's model for electromagnetic radiation and electromagnetism is based on these things: sources, fields, and matter. Okay, or materials. Okay. So we have the sources. Okay, that we have in this system can be free charges, which we can represent by this row of free charge density. They can also be currents, which are conduction currents, which are free charges moving most likely in a conductor. Okay, we can also have electric dipoles, a density of electric dipoles. Okay, and we can also have magnetic dipoles. Okay, so they're the sources. Okay, and we have this thing called a field. Okay, and we'll introduce it again later. But in summary, a field is some mathematical concept that models action on matter due to electrical source such as charge or resonance via an intermediate agent in the field. Okay, so a field is something that you have in place to model the interaction of one piece of matter on another one at a distance. Okay, that's what it is. And in our electromagnetic theory, we have two main fields. So we have something called electric field intensity. Okay, and we also have something called the magnetic field intensity. Associated with them is something called electric flux density and magnetic flux density. Okay, we'll see how they're related in a minute. Okay. So looking at what Maxwell's equations are, so these are the equations that allow us to model all of electromagnetic phenomenon. Okay, and they're given here in a macroscopic form. Okay, and you can see that they expressed in the language of vector calculus. Okay. So next week you'll get a bit of revision on vector calculus. Everyone pretty familiar with vector calculus here? Yes. You've all done the course on vector calculus before now, huh? Okay, well next week we'll have a bit of a revision. Okay, but they need to be expressed in the language of vector calculus. Well, they're most succinctly expressed in the language of vector calculus because two things, forces exerted on bits of matters by the fields have a direction and a magnitude, right? Okay, so they're vectors, and furthermore, we're looking at these forces and bits of matter that exist in a three-dimensional space. Okay, so to express all that correctly or concisely, we use vector calculus. Okay, we can express them as integral form as well. Okay, so in this form they're actually expressed at a point, but we can also express them over finite areas as well. Okay, So we incorporate, so we have our fields, which were E and H, okay? We said we had our sources, which were, J, current, charges, and these dipole moments, okay? We can also incorporate materials. So the final thing we need to incorporate into the model is materials, okay? And we do that through these constants. If it's linear isotropic, which means, the properties of the material are the same in all direction than linear, we can model a conductor by the conductivity, okay? And conductivity relates, the current density, flowing in the conductor to the electric field strength, right? And, if we have a dielectric, okay, which may also be a conductor as well, but, we relate this electric field flux density to the electric field by this thing called permittivity, okay? That's what relates those two together. That's how we describe matter in the actual equations as well. And for the magnetic fields, we relate the magnetic flux density to the magnetic field by this permeability. So it's again relating, introducing matter into Maxwell's equations via these constants, okay? And we also have this thing called the Lorentz force, okay? So, the force, we'll see that the force on a charge, Q, comes from something called the Coulomb force, which will be the one we'll start looking at initially, plus this other one called the inductive force. We'll look at how that comes about, plus this one called the Lorentz force, which is V cross B, okay? We also show that, this Coulomb force is a conservative force field, okay? And in fact, and that's the one that leads to potential difference, okay? That's this Coulomb field is actually the one that is what you deal with when you use circuit theory, okay? This is the only field that's relevant when you're working with circuit theory because it describes potential differences, okay? But, there's other parts of the electric field as well, okay? Not just the Coulomb field, okay? And we'll talk about, we'll look at, shortly we'll talk about definitions of what work and potential energy is, and we'll eventually show that, this Coulomb field can be described as the gradient of some scalar field phi, okay? And that leads to various things, okay? So, Maxwell's equations can be, or electromagnetic phenomena can be described by this set of four equations, which we typically call Maxwell's equations, okay? And, where we have two fields, E and H field, okay? But we can also describe everything by something called potentials, okay? And we'll also look at that. So, we'll see that there's two potentials that we're interested in. One's a scalar and one's a vector potentials, okay? So it turns out that the Coulomb field's a result of what's called a scalar potential. So a scalar potential is a function of is a scalar value of position, okay? And the vector potential gives a vector as a function of position, okay? So one's a scalar field and one's a vector field, okay? So it turns out that in some cases you'll see that determining electrical and magnetic fields from sources can turn out to be simpler when we employ this description of Maxwell's equations via potentials, okay? So this alternative, so it's like an alternative set of equations to describe electromagnetic radiation, okay? So the two, instead of having E and H, now we have and B and D. Now we have something called the vector potential field A, and also this other thing called scalar potential field phi, okay? And if phi and A satisfy these differential equations, vector differential equations, which look pretty awful, but if they do, then they describe everything in EMT for that system, given those sources and materials, etc. Okay, so we'll look at that later as well. Okay, so the models are equivalent. Okay, so you can derive E and B and eventually H from vector operations on A and phi. Okay, so we'll look more at that later. Okay, so it turns out that Coulomb field is the gradient of this scalar potential, and we have another part, as we were saying, to the electric field called the induced electric field, and that's related to the time derivative of this vector potential field. Okay, plus some issues with the Lorentz force. Okay. Okay, so what we'll do next is we'll go through deriving all those equations that we've presented there, okay, and applying them to various situations. Okay, so we'll start that now. Okay, so we've done up to we've just had a bit of motivation, introduction, and preview. Okay, so now we'll start at electrostatics. So the first part we're going to look at is electrostatics. Sorry, come on, give me a second. It always seems to. Okay, so first of all, recapping field. So when an event in one place has an effect on something at a different location, we talk about the events as being connected by a field. The field is a spatial distribution of a quantity. Okay, so it can be in general either scalar or vector in nature. Okay. So we also have to define electric charge. Okay, so obviously charge is generally considered to be quantized, and the quanta is generally taken as the charge on one electron. Okay. However, in this course, we're really looking at things at the macroscopic level. Okay. So we're going to assume that charge is continuous. Okay. So charge is continuous. So say we have, because we're not going to be dealing with charges anywhere near as small as the charge on one electron. Okay? So we can look at Coulomb's law. Say if we've got a charge Q1 at position, this is the origin, position R1, where R1 is some vector, okay, and we have Q2 at position R2, okay, then due to having Q1 and Q2 will see a force on it in the direction F12, this direction, vector direction F12, okay, and that force has a direction and a magnitude, okay, and that vector is given by Q1, Q2 times R2 minus R1 divided by 4 pi epsilon naught R2 minus R1, or the absolute value of R2 minus R1 all cubed, okay. So we can break out R2 minus R1 to a magnitude, okay, given by here, and also a unit vector in the direction, from Q1 to Q2, okay. We can break it up like that, and then we see that, it's in fact an inverse square law, okay. Coulomb's law is an inverse square law, okay. So this guy, like Coulomb, he used to work on these things called torsion balances, okay, and he used to get little bits of pith balls. Is like pith comes from the parts of sort of fibrous plant, and coated with probably a bit of conductor and charges on them, by rubbing silk or something on them, and then he'd actually put them different distances away, and because he had very precise measurements of force, he could, by this torsion balance, he could measure the forces, and he worked out these particular laws. Okay, so it's an inverse square law. Okay. Okay, so the magnitude is this Q1, Q2 on 4 pi blah blah blah, and the direction is R12. We can look at the magnitude of that compared to gravity, right? So if you had two protons 1 centimeter apart, then it would be the force, if you work it out, is 2.3 by 10 minus 24 newtons, right? If you have two neutrons 1 centimeter apart, then due to gravity, it's about 2 by 10 minus 60 newtons, right? So the electrostatic force is about 10 to the 36 times stronger than gravitational force. Okay, so it's really a large force, and you can get a better feeling of that if you consider the force on two charges which are 1 kilometer apart, and the charge is the charge that you'd have if you take all the conduction electrons from 1 gram of copper. So you have a gram of copper, it has part of that consists of conduction electrons, right? So if you took all the conduction electrons out of that gram of copper, and you had a positive charge placed at one point and a negative charge or another positive charge a kilometer apart, then you get a thrust that would be given by this 2 by 10 to the 10 newtons, which happens to be about 2,000 times larger than the maximum thrust of a Saturn rocket that sent man to the moon. So really, a very, very strong force indeed. Okay. So we've got Coulomb's law. Okay. So if we place a charge Q at the origin, right? Okay. We place another charge. We call it a small test charge, called QT, at distance in a position R from the origin, okay? So that little test charge is going to experience a force, right? We know what that is, okay? Force on QT is going to be Q times QT R on 4 pi epsilon naught R, the magnitude of R cubed, right? Which is, again, proportional 1 on the magnitude of R squared, okay? And we define the electric field produced by Q at a point in space as the force per unit charge acting on a test charge QT at that point, okay? So, it's EC is the limit, okay, of F Q of T divided by QT as QT tends to 0, okay? And so that's going to be, if you did that, you'll see that's Q R 4 pi epsilon naught on magnitude of R cubed, right? Okay, that's if it's located at the origin. If this cube was not located at the origin, it was located at R dash and begin by this, right? Is that clear? So we also consider that that charges, the force from a number of charges adds up linearly. So superposition can hold, right? Okay, so the field at some position R, due to a number of these charges, it's just going to be the sum of the electric field contributions from each charge individually. Okay, so you can do an example if you really want to. So here we have we're looking at the electric field at, let's say, one point in Cartesian coordinates 1, minus 3, 7. Okay, in the x, y, z, and due to this 5 nanocoulomb charge at 204 and minus 2 nanocoulomb at minus 305. Okay, and you can just put that in, do the maths, and you end up with the electric field to be this. So you can see that electric field is a vector. Okay, so it has a magnitude and a direction. Okay, so these are AX is a unit vector in the x direction, AY is a unit vector in the y direction, AZ is a unit vector in the z direction. Okay, so it's a vector. Okay, so we can add up. We can find the E field from lots of charges distributed over anywhere. Okay, but so then once we have that, we can then then consider volume charges, so that if we have a volume which has some distribution of charges in it, so we have like a charge density. Okay, so by looking at just a small, infinitesimally small area of that volume dV dash, okay, and multiplying that by the density of charges at that point, we get the amount of charge in that small volume. Okay, and then we can find the E field at, let's say, some point P. Okay, by just integrating over that volume rho dV and times the Coulomb's law. Okay, so that clear? So again, we can also consider charges that are distributed on the surface. Okay, so instead of a volume, we have a small piece of surface. Okay, and the amount of charge contained in that piece of surface is the surface charge density times the ds. Okay, and then again, we can, to find the E field at a particular point P, we can just integrate all the contributions from all these points on the surface. Okay, and line as well. We may have charges that are distributed on a line. Okay, so then you might have a charge density in coulombs per meter. Okay, and then it will be every small section of that little line dl times the charge density will give that small amount of charge at the point. Okay, and we can integrate that over the whole line to get the final E field at position P. Okay, so electric field it's a force field. Okay, it's like gravity. Okay, if a body being acted on, a force is moved from one point to another, then work is done. Okay, so if you think about gravity, if I've got this pen here and I want to move it upwards, then I have to apply work. Okay, I have to do work to move against that force. Okay, so and the amount of work I supply is this dW is the differential amount of movement I make. Okay, in this case going up, and time with dot product with the actual force I supply. Okay, so the amount of movement I make in the direction of the force I'm applying. Okay, that's the definition of work. Okay, so and you can see that's going to be minus dr times EC when we're talking about the electric field, because it's the work you put when you put work in, it's against the force of gravity or against the force of electric field. Okay, so that's why I've got a minus sign there. Okay, and again it's a dot product. So if we're talking about gravity as an example, I need work to lift it higher. I need to put work in. Okay, but if I'm going from side to side, okay, I'm not pushing against that force. Okay, the only work I need is to overcome air resistance. Okay, or something like that. Okay? But so that's why we have the dot product there. Okay, because the work done is the work that you put in to move against the force. Okay, and if you're not moving in the direction of the force, okay, if you're moving perpendicular to the force, then you're not putting in any work. So it's a small amount of. Okay, so we're saying because these things would change as distance, right? I mean, we're just saying if you're putting a little bit of work, you just move a little bit of distance, and that little bit of work you put in is that. Okay, I mean, if it was a constant force over a large distance, you could say, well, total work put in would be this. Okay, but obviously later these will be involved in integral equations. So to get the total work, we'll do an integral from point A to point B. Okay, so we've got an idea of what work is now. Okay, so then we're going to start talking about integrating that work. Okay, we'll see it's from infinity. Okay, but a bit more, and then that will lead to something called potential, electrostatic potential. Okay, so here we have a charge Q, which is sitting at position R dash. Okay, and we have a little charge here P at position R. Okay, and we move that charge at P from P to this point S. All right. Okay. So we can say, if we do that, the work done is the integral of this EC dot dl along that path L1. Okay. So at each point, we have in that path we have a little bit of dl. Okay, and dl is a vector, so it has the magnitude of how far you move. Okay. It also has the direction. The direction is basically the tangent at each point of the curve, because it's the direction of that curve is going in at that point. Okay, so typically the tangent, so it'd be going like that at this point and going like that at that point. Okay, and so it's a dot product. Okay, so between whatever the field is at this point and dl. Okay, it'll be a dot product, and it's integral, and we've got minus sign because remember how we define work. Okay, so we can consider another path. Okay, and we can do the integral, but going from P again to S. Okay, so can anyone tell me what's the relationship between this W1 and this W2? The same, right? They're the same. That's the important thing. Okay, because it's a conservative field, what we call a conservative field, the electrostatic field is a conservative field. We'll see that some of the other electric fields aren't conservative, but the electrostatic field or Coulomb field EC is a conservative field. Remember that, you use that a lot. Okay, so and that also means that any line integral over a closed path has to be equal 0. Okay, so integral over EC dot dl, and it's a closed path, so you go from say P to S and back to P again, it's going to be 0. Okay, and force fields, which this is true, are said to be conservative. Okay, so happens that, so, when you do your revision, this is also the information sheet that you get. It should be on the LMS. If you look on part 2, you'll get an information sheet. So part of it, you've got all these vector calculus identities, okay? And, you've got the definition of this del function here, okay? So when you do, so you can work out what you get when you take the gradient. So, when you have, put it down here, lucky, isn't it? So say we've got phi, which is a scalar function, right? Okay, so that means it gives a single value at particular x, y, z point in space. So you can see that when you take this del of phi is called the gradient of phi, okay? That will give, and this is the definition here of this del operator, it gives, the del of phi is a vector, right? Okay, you can see that's got something in the ax direction, something in the ay, and something in the az direction, okay? So it's a vector, okay? And we can see that, we also got another identity here, that this other operator here, this del cross, called the curl, okay? You remember, does everyone remember the curl and of a field and that? Do you remember that? No? You better, you're going to use it. The curl and the gradient are used a lot, okay? So that's also, that's basically the cross product of this del operator with, curl of A is, say we have a vector field A, is just effectively the cross product of this operator with A, okay? Do I have it here? I don't think I have it in, because it's fairly obvious in Cartesian coordinates, but anyway, you can multiply all these things out by using these particular definitions, and one of the things you can see is that if you have the curl of the gradient of a scalar field, then it turns out that always comes out to 0, right? Just from the definitions, okay. And we also have something called Stokes' theorem that relates. So say if we have a surface, okay, in space, okay, and we have a boundary around it, okay, of length L, and we have little sections dl, and this is ds. So these are this surface ds, okay. So it turns out that there's a relationship between the integral. So we have a vector field. So we have a vector field A, okay. If we take the integral, around the boundary of this surface, okay, it happens to equal the integral over the surface of the curl of the vector field, okay. And so in this situation, if we have, we know that the integral around any closed path of E C dot dl equals 0, okay. And we can see here if we have if we had A to be equal to the gradient of some scalar function, then this curl of the gradient of scalar function is always 0. So that means that that integral would also be 0, right? So if the curl of the gradient of a scalar function is 0, okay, and we take an integral over some surface, okay, then that will also be 0, okay. And so if we take the integral of the curl of some vector function, that vector function is given by the gradient of a scalar function, okay, then that integral over that surface is going to be 0, and correspondingly means that the integral of the line around the line, closed integral around the line that bounds that surface is also 0, right? That's from Stokes' theorem, okay? So that means that we can express this Coulomb field as the gradient of a scalar field, okay? That's why we can express the Coulomb field as a gradient of a scalar field, okay? And so the curl of the Coulomb field is equal to 0, okay? Of course, from here, okay? Is that clear? Okay. So and this scalar field phi, okay, it's known as electric potential, okay? And the Coulomb field is equal to minus the gradient of this electric potential, okay? So any questions on that? It represents at any given point the potential energy that a positive unit of charge would possess if it was located at that point, okay? And it's something that's measured in volts, okay? Other things will be measured in volts as well, but the Coulomb or electrostatic potential is measured in volts, and this is the potentials and potential differences that we have in circuit theory, okay? The potential energy of electric charge represents net amount of work that the Coulomb field would do on that charge as if it was taken away to any point at which the potential is 0. So if you had some charge at the origin, you had some test point, you had some point here away from that, and the potential would be basically the energy that's going to be put in by the Coulomb field as that test charge is pushed out to infinity, okay? So generally we take infinity as where the potential goes to 0, because that's infinitely away from any other charges in the system, okay? So if we have some finite system that has some charges, then obviously the electric field and the forces at infinity are going to be 0, right? Because they'll be infinitely away from the actual charges that we're interested in, okay? So maybe we'll just finish off on potential difference, okay? So if the unit positive charge, so we've got got some E field that's caused by some charges or distribution charges at some points in space. Okay, but we have a unit test positive charge. And we take it from point A to point B. Okay, along any path. Okay, okay. We say L1. The work done is integral of E dot dl along this path. Okay, and we can say potential difference between the 2 points A and B. Okay, you should know this notation quite well because it's going to be important. Is the integral of minus integral from A to B of EC dot dl. Okay, and because we could take any path we like. Okay, that's also the same as the integral of going from A out to infinity and then coming back in from infinity to B. Right, because we can take any path. Okay, so if we sort of rearrange that a bit, it turns out that is phi B, the absolute potential at B minus this absolute potential at A. Okay, so if B was at a higher potential, then you can see the potential difference would be positive. Okay, so and that's the potential difference that we see in circuit theory. Okay, so we'll go through an example. We'll stop there. It's about time, and tomorrow we'll go through an example of doing that. Just get a bit of feel of it. Okay, and next week you should start on there'll be vector calculus revision for the prac class. So be sure to do that if you're not all up to scratch with vector calculus. Okay, so thanks.